Okay, so MATLAB finite element method programming. This is an overview. So in this overview, I'm gonna go over what we need to do in order to get a solution from a given problem. Alright, so this could be any problem. In our case, we're going to do linear elasticity, but this can be also heat conductivity or any other problem. So the first thing we need to do is create a mesh. Once that is done, we need to define boundary sets from this mesh. That means that we need to identify nodes where we will be applying boundary conditions, and also we need to identify certain nodes where we will be applying loads. Alright, from that we need to assemble the nodal matrices, and basically we're looping over all elements and we're creating the element stiffness matrix. Okay, so for a linear elasticity problem, this really is the stiffness matrix. For a heat problem, we still call it the stiffness matrix, but it contains other operators now. Alright, so in order to create this element stiffness matrix, we need to define element base functions, and these depend on what kind of mesh we have and what kind of approximation we want to have. So, I mean, we could have, for instance, we could have linear triangles. We could have second order linear triangles. We could have bilinear quadrilaterals, or we could have higher order elements as well. All right. Depending on the base function and the actual problem order, the highest polynomial order, we need to choose a appropriate numerical integration scheme such that the integration is computed exactly or with a little error as possible. Alright? Okay, once the element stiffness matrix is created, we need to create the element load vector. Once that is done, the element mass matrix is created. For certain problems, this is not needed, so this might be optional. Alright, so now that we have assembled all of these element stiffness matrices, load vectors, and mass matrices into the global nodal fields, we end up with at least the stiffness matrix and the load vector. Maybe not the load vector, but yeah, it depends on the problem. Maybe we just have the stiffness matrix. Sometimes we have the load vector and the mass matrix as well. What we now need to do is we need to reduce the linear system. That means that we apply the boundary conditions, and we either calculate from the boundary conditions, we calculate the loads, or we just reduce by removing the equations that are not needed in order to get a reduced linear system that is solvable. And once we have this reduced linear system, we can solve the linear system in order to get our output, our solution field. Now, imagine you have S times U is equal to F. This is the solution field is implicitly defined here by U. What we do is we take use Gaussian elimination or LU factorization or any other methods that are appropriated. MATLAB does this under the hood to get the solution field, in this case U. So once we have the solution field, we could either go on, if we have a dynamic problem, the solution field will be our starting point in order to do a time stepping scheme, which you will do, and I'll explain that later. Or we can do the processing of the resulting solution field in order to compute stresses, strains, or just displacements.